patterns in the periodic table. So you don't have to copy this picture down to the periodic table. Last year, what I did was I gave you a blank copy and we did a whole bunch of demos. And if you remember in the first column, I threw some lithium in some water and it kind of bubbled and smoked. Then I threw sodium and it kind of exploded, caught on fire. Then I threw potassium and it made a huge kaboom. So what we find is as we go down the periodic table, elements become more reactive. And in fact, this first column here is very, very reactive. Then we went to the second column and I put some magnesium ribbon in water, not too much happened. Calcium, it bubbled more. So in the second column, things are also reactive, not as much as the first column. So in the first column, very reactive. Second column, not too reactive. If we go to the other side, the second last one is something called the halogens. And they're very reactive, very, very reactive. There are salt formers. And the very last one are our noble gases, and they're very stable. And we're going to talk about why they're stable. So that was just a quick review of last year. So let's go through a couple more things. If you look at the picture, it's pointing to the right and said those are periods. So if you start on the right and you move all the way to the left, everything in that row is considered a period. So it says a row of elements on the periodic table is called a period. Then if we go up and down, the columns. So it says a column of elements on the periodic table is called a group or a family. Sometimes we call them families, sometimes we call them groups. So period is to the left and right, the whole row. Groups or families, we go up and down. And there's 4 main groups that you should be aware of. So the very first one is something called the alkali metals, group 1. And we don't include the hydrogen. The hydrogen's there because of how many electrons it has. So if we go down the first column, that's actually called the alkali metals. And they're usually soft. I don't know if you remember this, but the lithium, sodium, potassium, I just cut it with a butter knife. They're very, very soft. They're malleable. They're very, very shiny. And they're extremely reactive with water and the halogens. So that's our first column. So they're very, very reactive. They're soft. They're shiny. And they have a high luster. Luster means how shiny something is. So the second one, let's move it up here. The second column are the alkaline earth metals, or group 2. When you look at your periodic table, what you'll see are numbers above them, above each group. So there's a 1, a 2, a 3. So group 2 are the alkaline earth metals. Alkaline earth metals are also reactive. They're not as reactive. But they're also reactive, not as reactive as the first column, but the second column. All right, next one I want to look at is the second last column. These are the halogens. So the halogens, halogens is group 17. They're very reactive and very toxic. Okay, so very, very reactive, very, very toxic. And the last column are the noble gases. The noble gases are the most stable. They're very unreactive. They're usually colorless. When we look at the electrons in the outside shell, the outer shell or the valence shell, they're full. And that's what makes them actually very, very stable. So they're very stable, unreactive, colorless is the very last column. There's another thing we talked about in the periodic table, and it almost looks like there's a staircase. The staircase separates the metals and the non-metals. So on the left side, all this blue stuff you see here are considered metals. On the right side, there's these pink ones here, not very many of them, they're the non-metals. And then along the staircase, there's some elements colored in green. Well, the green indicates, well, we're not quite sure. They got properties of metals, they got properties of non-metals, and we call them metalloids. So the metalloids, they're kind of along the staircase. They have properties of both, like metals and nonmetals. An example would be silicon. Silicon is a shiny silver rock. It looks like a metal, except it doesn't conduct electricity. It's kind of interesting. So it looks like a metal if you were just to look at it, but one of the properties of metals is that it conducts electricity. It doesn't conduct electricity. The other thing about silicon is it's very brittle, and metals are not brittle. So the metalloids kind of have properties of both. So a couple things to review. The first column is the alkali metals, extremely reactive. The second column, alkaline earth metals, they are reactive but not as crazy. They'll just like bubble a little bit like the magnesium and the calcium. The halogens, there are salt formers. They're very reactive as well, very, very toxic. The last one is our noble gases. Noble gases have filled outer shells, which makes them extremely stable. They don't want to react with other elements. And then finally, we have the staircase that separates the metals and the non-metals, and things along the staircase have properties of both, so we give it a special name called metalloids. So we need to know the difference between a metal and a non-metal, and each have specific characteristics. So here's the property of the metals and the non-metals. For instance, all the metals except for mercury are actually solid at room temperature. Non-metals can be at room temperature solid, liquid, or gas. Another property is luster. Well, metals tend to be shiny. Non-metals tend to be dull, so the opposite of shining. Metals tend to be malleable. They also tend to be ductile. So malleable is the ability to be hit with a mallet, a hammer, and flattened out into sheets. If you hit something with a hammer and it shatters, well, it's not malleable. So metals tend to be very malleable, and that's why we like them for jewelry. You can like stretch them out into necklaces and bracelets and rings. Non-metals, if they're solid, tend to be very brittle. So if you hit it with a hammer like silicon, it actually shatters. So that's why we think, oh, well, maybe silicon is not a metal. It's actually a metalloid. Electric conductivity. So does it conduct electricity? Does it allow electricity to flow through it? So inside all our wires that hook up our phones, our televisions, electricity into the house, is a conductor, and it's always a metal. Usually it's aluminum. It can be copper. Copper is more expensive. So copper, aluminum are the main ones, but all metals do conduct electricity. We surround the outside of all our electrical wires with something called an insulator that doesn't allow electrons to flow through it easily. That way I can handle a wire that's, say, plugged into my toaster or my telephone without being electrocuted. We also find that non-metals tend to be insulators. They don't conduct electricity very easily. So I'm going to put two objects down here, and I have this shiny silver ball, and I'm not going to do it, but if I hit it with a hammer, it will actually flatten out. I use these in my roller coasters, and part of that project was that there has to be an electrical component, so it actually triggers an electrical device that allows current to run through it. So this is an example of a metal, and I can just look at it and realize, oh yeah, it's hard, it's shiny, it's silver. I know it conducts electricity. If I look at this other object here, well, it's dull. It's just a stone I found outside. I bet if I hit it with a hammer, it's actually going to shatter. If I run a current through it, it doesn't actually conduct electricity. So here's an example of a non-metal. So the big things is metals tend to be solid, shiny, they conduct electricity. If I hammer it, I can hammer it into like sheets, it makes it malleable. There's no way I can like hammer that into a thin sheet or make a ring out of it. It would just break. Atomic structure. So what we learned last year was that everything's made out of atoms, and the center of the atom is something called the nucleus, and it's actually Latin for kernel. So the nucleus, okay, contains the protons and the neutrons, and most of the mass of the atom is located there. It's all concentrated. Around in these orbits or circles going around the nucleus are the electrons, and they actually follow a path which we call the shell. So it says here, recall that an atom's atomic number tells us the number of protons it has, and its mass tells us the number of protons and neutrons added together. We learned how to draw these Bohr-Rutherford diagrams, and Bohr and Rutherford are actually names of scientists. Our models used to represent the arrangement of electrons in orbits around the nucleus of an atom. And there's a couple little things to remember. So I always use PEA, the vegetable. Okay, and what it means is the number of protons, electrons, and the atomic number are all the same. So if you have 5 protons, that means you have 5 electrons, and the atomic number is 5 as well. So if you know one of them, you know the other 2. So let's say the atomic number was 12. Well, that means you have 12 electrons and 12 protons. Now up here, it says the atomic mass is the number of protons and neutrons. So there's a formula. So if you know what the atomic mass is, well, that's the number of protons and neutrons added together. So if you got the atomic mass and number of protons, we can calculate how many neutrons there are. I also said that the electrons travel around and around in these shells. Well, there's only room for 2 electrons in the first shell, 8 electrons in the next shell, 8 electrons in the next shell. It gets a little complicated after that. So just remember 2, 8, 8. And what I would like to do is draw the Bohr-Rutherford diagram for sodium right now. So first thing you do is you write down the symbol for sodium, which in this case is Na. That's the symbol we use for sodium. And you look in your textbook at your periodic table. So when I look at my textbook at my periodic table, the number on the bottom, you have to look at the guide. So the guide, it says the atomic mass is the big number on the bottom. The atomic number is the number in the top left-hand corner. So the atomic mass is 22.99. We're going to round that to 23. And the atomic number is 11. So we're going to write that down on our page. So I write down the symbol, and then I write down 11 at the top, because that's where it is on my periodic table, and 23. So first thing I'm going to do is write down my PEA, and I actually do want you to write it down. So you're just going to write those initials down, PEA. P is number of protons, E is electrons, A is the atomic number. Well, my atomic number is 11, so that's 11, which means I have 11 electrons. It also means I have 11 protons. I also have a formula. So my formula is the atomic mass is equal to the number of protons plus the number of neutrons. Well, my atomic mass is 23, so I just write down 23. Number of protons I know is 11. And then I need to figure out the number of neutrons. So 11 plus something gives me 23. And actually 11 plus 12 gives me 23. Another way I could do this is just go 23 minus 11. That gives me 12. So now what I can do is I can start drawing my electron, or sorry, my atom. So first thing I do is draw a circle for the nucleus. And inside the nucleus, I know I have the protons and the neutrons. Well, I have here 11 protons. So I'm going to write down 11, my pen worked, P. There's 12 neutrons, so I'm going to write down 12, N for 12 neutrons. And now I'm going to start doing my electrons. There are 11 in total. So in the first shell, there's 2 ways you can do this. You can put the dots side by side, or you can put one at the top, one at the bottom. I like putting one at the top, one at the bottom. Now that's a filled shell. So I can't put any more there. I need to move to a second shell. So you just draw a second shell all the way around. And when you put the dots on, which are the electrons, they go clockwise. So we start at the top and you move clockwise. You put one at the top, one at the side, one at the bottom, one to the other side, then you start over. Once you get to 8, which means 2 times around, you need to start a new shell. So always start at the top. So we already have 1, 2, that's number 3, number 4, number 5, number 6, number 7, 8, 9, 10. And the reason we kind of clump them in twos, it just helps us visually look at it quickly and see how many there are. And no one's, we've gone around twice, everything's doubled up, it's filled, I need a new shell. So I put one more shell, and that would be number 11 at the top. So when you do this, I'm looking for you to write down PEA, write them all in. I need the formula where you calculate the number of neutrons. You draw your nucleus first, put down the number of protons, neutrons, and then start with your shells. Remember, you can only have 2, 8, 8. If you need another shell, you can add another shell past that. That's fine. And when you put the little dots on, which are the electrons, the first one, there's only 2. You put one at the top, one at the bottom, and then you do it like a clockwise motion. 1, 2, 3, 4. Start over. 1, 2, 3, 4. Then it's full. Move to the next one. I wanted to do the Bohr-Rutherford diagram for another element, and I'm going to pick oxygen this time. So oxygen has an atomic mass of 16 and an atomic number of 8. If you forget which is which, there's always an index, which is on the other side, that tells you, oh, look, atomic mass, it points right at it. Atomic number points right at it, so you know which one's which. So my numbers for oxygen are 8 and 16. So let's do that. So I'm just going to put the symbol for oxygen O down. And I put 8 in the top corner, 16 at the bottom, so I know how many of each I have. First thing you do is you write down your PEA. So that's protons, electrons, atomic number. Okay, and they're all the same. So my atomic number is 8, which means I have 8 electrons and 8 protons. I also have a formula. Okay, my formula helps me figure out how many neutrons I have. So my atomic mass is equal to the number of protons plus the number of neutrons. Well, in this case here, my atomic mass is 16. Number of protons is 8 plus some number of neutrons. So I have to ask myself, 8 plus what gives me 16? Or I can just go 16 minus 8. And the answer is actually 8 as well. So in this case here, the number of protons and number of neutrons are the same, but they don't have to be like in our first example. Now you're going to draw the nucleus with just a circle. And inside the nucleus, you're going to put down how many protons and neutrons you have. So I have 8 protons and 8 neutrons. There's 2 ways of doing this. Sometimes people put down, okay, protons equals 8, or you could just go 8p. I'm okay with either one. I understand what both mean. All right, let's keep going. I've put in my protons, I put in my neutrons, so now I need to start putting in my electrons. In the first shell, I'm only allowed 2, so I put 1 at the top, 1 at the bottom, but I need to get to a total of 8. So I draw a new shell in, and you start at the top, and then you move clockwise. So I got 1, or sorry, I'm at 3. 1, 2, 3, 4, 5, 6, 7, 8. And then I just stop. So some basic facts about atoms. So the protons and the neutrons are found in a very small, dense nucleus. So the nucleus is the center, and that's where all the protons and neutrons are found. Electrons are found in specific orbits shown as a ring around the nucleus. And what's interesting is I've been teaching this for over 20 years, and it was only about 5 years ago that we were first able to see a photograph at the level of technology with these electron microscopes of an actual atom. And they did the hydrogen atom, they were working on the helium one, and you actually see the center, the core, and then you see the path that the electron's traveling around and around it. And that only happened a few years back. So we know that the protons and the neutrons are in the center. The electrons are going around these orbits on the outside. Other things about elements. So alkali metals are highly reactive because they contain 1 electron in their outer shell. So what all the elements are trying to do is to have a filled outer shell. So the alkaline metals, because they have 1 extra electron in their outer shell, they're trying to lose that. In order to lose that, they react with another element and they basically give it up. So if we go back to our example of sodium. So for sodium to be happy, he needs to be happy like the noble gases. He needs to have a filled outer valence shell. There's 2 things that can happen. He can either lose 1 electron or gain 7. Well, losing 1 electron is much easier to do that. So it's quite happy. Sodium's quite happy to react with any of the halogens, because that's a very, very easy transfer, because a halogen needs to gain one electron, okay? And the alkali metals need to lose one electron. So that's why they're so reactive, because all it has to do is lose this one electron, and it has a filled outer shell. And that's what makes them reactive. Noble gases are very stable because they have filled outer shells. So they don't want to lose or gain any electrons. Okay, they already have these filled outer shells, or they're very, very stable. We call that the valence shell, the outer one. The number of electrons in an atom's outer orbit affects this reactivity of that element. So again, because alkali metals need to lose an electron, they're very reactive. Noble gases have filled, stable outer shells. They're very stable. They don't want to react with anybody. So we look at how many electrons are in the outer shells, and that tells us how reactive it's going to be. It says, in general, atoms tend to react with other atoms in order to have filled outer electron orbits. And that's the whole point of the chemical reactions. They're either giving up an electron, gaining an electron, or even just sharing an electron. That can happen as well.